a massive math problem. You might have heard me talking about it, maybe complaining about it a little much. But this is our work for the last 3 weeks. And so, first of all, I just want to give you a little visual aid here. This is not actually the diamond that we're going to be using, obviously, because diamonds are expensive. But I just want to give you a good visual aid. This is actually what we have set up in the lab right now to test what the frequencies are. And here we have, you see, a 3-dimensional coordinate system. We have an X dimension, Z dimension, Y dimension, just your traditional X and Y going horizontal and vertical. And then Z is coming straight out. Sorry. And we have several modes of oscillation. As you can see, we have oscillation on the Z-axis, which is just going back and forth, out, out and in. Rotation about the X-axis, which if you have the X-axis here, it's just going to go back and forth like this. The Y-axis is going to be similar to the X-axis, except for it's around this axis, so it's going to go like so. And the Z-axis is going to stay in the X-plane, but it's going to rotate like this. So you'll see the diamond rotating from a front view. First, I'm going to cover the first mode, oscillation on the Z-axis, which is, here are some measurements of just what lengths we have available to us and what we know already. So we have the wire length, which is this right here, and we call that W. The diamond length is this right here, and this is A. Since it's a square, that's the length for both the horizontal and vertical sides. The distance between the wire joints is this right here, and that's going to be called S. And the mass of diamond is M. The velocity of a wave traveling along the wire is V. And all of these will come in later in our equations when I'll talk about that in a couple of slides. So this is the first mode, oscillation on the Z-axis. As you can see, we have some tension components going on each of the wires. I think I forgot to mention those before. But oscillation on the Z-axis is going to exhibit behavior as if you hit it right in the center. Now, keep in mind we're not actually hitting it with anything, because the electrons that are hitting the diamond don't have enough force or energy to actually move the diamond. It's just earth vibrations and whatever's around it. But it would appear as if you did hit it directly in the center there. I have just a visual aid here. This is a side view, so if we just turn it around 90 degrees, let's see if this works. There we go. So as you can see, it's going back and forth, and what we needed to do was measure the frequencies. And to do this, before we got into the lab, we did some calculations, and I'm about to show you that on these next couple of slides. This is our last 3 weeks, or part of our last 3 weeks. Basically what's going on here, you saw that the lines, actually I'll go back and see if I can get that again. So you see right here the lines are curved. And initially what we did, we calculated with a straight line because we thought they might just be, we could treat them as rigid rods, so they were just moving like this. But we found out it'd be more accurate to test them as if they were curved, which they are. So because they're curved, we have to use a sine function in order to represent their shape. And basically all this is saying is the shape where the diamond connects to the wire is represented by all these equations, and ultimately we get down to right here. This is our baby. This equation right here. And what we're trying to calculate is the restoring force, and through this we can get the frequency that we need to find. So it's related to this restoring force. We do some math here, a bunch of calculus. Anyone who's been in calculus? It's fun stuff. But here we have omega. You see that omega weird W character right there. And that measures the frequency in radians per second, which is just rotations. If you took a frequency and multiplied it by 2 pi, which I'm not going to go into that. But if you take that general formula right there for omega, is omega squared equals k over m, where k is a spring constant if you treat the wires as if they had elasticity. And the equation that we got linking that to this equation right here is this right here, omega squared equals all of that. I'm sure you can read it in stuff like. the way we solve that, since, here I'm going to go back, sorry. You see there's an omega squared over there, but there's also an omega in the cotangent function on this side. So we can't just algebraically solve it. So to solve it, find frequencies, we graph the two against each other. And we have the omega squared graph right here, which is just this right here, and then the cotangent, omega cotangent of omega is this right here. You see the continuous line pattern, and it's going to go through that all the way to infinity. And so you see there's going to be infinite intersections because that one goes on to infinity, and that one keeps coming down repeatedly over infinity. So there's not one frequency, there are actually many infinite frequencies. But for each mode of oscillation, there's going to be a vast difference from this first intersection to the second one, and then the rest are going to be pretty similar. And let's move. All right, the next mode, the rotation around the x-axis, which I talked about before, is just this right here, and this is as if you hit it right on the top or right on the bottom. But again, it's not being hit actually. So let's see, I believe I have an animation. There we go. Now again, you're going to see those curved lines, and I'm not going to go through the math because it's actually very close. But that generic equation for omega, where omega squared equals k over m, is just going to be there's going to be a coefficient applied to it, which I'll talk about later. Whoa. Okay. The y-axis mode is also quite similar. The rotation about the y-axis. I'm just going through all these modes and I'll cover them all as one briefly. So the y-axis mode is as if you hit it on the side, and this animation is going to be very similar, you'll see. Right. Now, if you can imagine, the wires are coming out, right. They're going to be right here, and they'll be twisting. Okay, they'll be twisting as they rotate away from their initial position, so they'll be coming more like that as they get towards the outer edge of their rotation. Our final mode is going to be rotation about the z-axis, which again, I'll remind you, is just in plane like this, so you see it rotating. And it's as if you hit it on the side here. It's going to be one of those. And you'll see that these wires are going out extremely, like, these have quite a bit of slack because they're going closer to the point of connection, and these are stretching out quite a bit. And that's because all of these diagrams are very exaggerated, because in reality, these oscillations are going to be very tiny oscillations with very little motion involved. And this mode actually isn't allowed just physically, at least not to this extent, because this wire stretches out, and the tungsten wires that are supporting the diamond they don't have that kind of ability and elasticity to stretch out that much.